Okay, quotient property of radicals and rationalizing denominators. This is the last little bit we got to do as far as this radical operations lessons go. You used to know how to do this. Maybe you still do. At least you used to do it with the simple ones like the one on the bottom. What do you do down there? Anyone?
Multiply by the reciprocal?
Nope.
Multiply it by itself.
Nope. There we go. Multiply by the denominator. Times by rad 5 over rad 5. Okay? Which gives you a numerator of what? Three rad 5. Denominator of rad 25. And then the square root of 25 is what? 5. So you get 3 rad 5 all over 5. Okay. What was that called? What's that process? Rationalizing your denominator. What's the goal of rationalizing your denominator? What's the end game? Why do we do this? Why are we doing what we're doing? There you go. So there's no root in the denominator. Now, why did you multiply by a rad 5?
Because it's equal to 1.
No. Morford, stop mumbling. I know, but I thought you had an answer, so I couldn't understand your mumbling. There you go. So you get rid of the rad 5, because rad 5 times rad 5 gives you rad what? 25, which is a perfect square. Okay? All right, see that? Okay. Now, just like the other day, you're going to have to take that logic and apply it to different scenarios that you haven't seen yet. Okay? Which makes this become a little tougher. All right? Becomes a little tougher. Okay? But that's basically what that white box says. All right? So let's go to the next one. Is this what I think? Yeah, let's do this first. Okay. All right, so we have the big square root of x to the 6th over y to the 7th, okay? First off, I'm going to write that as two little square roots, okay? That's a legal move. Square root of x to the 6th over square root of y to the 7th. All right. Now, both of those, you can what? Simplify, good. Square root of x to the 6th can become what? X to the 3rd, good. What about y to the 7th?
X to the 3rd, rad y.
Good. Okay. X to the 3rd over y to the 3rd, rad y. Now, if that ended up being perfect where you ended up without a radical in your denominator, woohoo, we'd be done. But, we're not done. Okay? So we still have to get rid of the square root. So what are we going to multiply by? A rad y. Good. Okay.
So it's just like adding another step.
Okay. Which will become, all right, so you have in the numerator, you're going to have x cubed square root of y over the bottom. Okay, I'm going to kind of show a mini step here. All right. The bottom's going to become y to the 3rd square root of y squared, right? Square root of y squared is what? Y times y to the 3rd, y to the 4th. Can you simplify these y's? No. Good. This one's in the radical. These are not. That's your answer right there. So it's basically, once you move the variables and you keep it square roots, it's kind of the same thing as numbers, except you can simplify the variables first most often, and it adds a little bit of an extra step because you might have some extra simplifications to do. All right, Lex.
So for these problems, they're just going to give you like that and say simplify?
Yes.
And that's your answer?
Yes.
Okay.
Yes.
Is it ever going to be put into like a problem?
This is called editing on the fly. Wow. Everybody good? Let's go, how about 2 over the cube root of, let's make it easy, 3. Let's stick with this as your logical approach, okay? So if last time when we had that 3 over rad 5, actually, you know what? Let's change, well, you already wrote it down, we'll keep it this way. When we had the 3 over rad 5, we multiplied both top and bottom by what?
Rad 5.
Rad 5, okay? So let's do the same thing here. Let's multiply top and bottom by a cube root of 3, yes? Okay. So cube root of 3, cube root of 3, which equals 2 cube root of 3 over what?
Cube root of 9.
Cube root of 9. Okay, legal steps there. Everybody see that? Yeah. All right, now what?
Do you have to do it again?
Yeah. Why?
Because it's cubed.
Because you got a cube root of 9 now.
Yeah,
9's not a perfect cube, is it?
No.
Okay? So you have to make the denominator become a perfect whatever index you're working with.
So if it gives you like to the 6th root, you have to do 6th root?
Yes.
And do we have to
Okay.
show each
No.
root?
Gosh, no. Gosh, no. 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 This is what I want you to do. Okay? I wanted you to do this just so you get the logic of it. Everybody see that? Okay? I'm going to take that same problem down here. So 2 cube root of 3 times red, because I always do red from your head. Okay? Now, here's why I gave you that pop quiz today. Because here's why I need you to know. Okay? You have a cube root of 3, and you kind of have to change to make I think anyway, to make these problems be the easiest they can be. You kind of have to change your thinking a tidbit. Okay? You have a cube root of 3 here. Okay? How many factors of 3 do you have right now?
2. Wait.
Back to the original. Right here, we have how many 3s? 1. Don't count the index, right? Index is notation. We have 1 3. Okay? Everybody see that? How many do we need total?
3.
We need 3. So we have 1, we need 3. How many do we need to add? 2.
Oh, okay. Yeah.
2. You do that to top and bottom. Okay, now that's where you shake it out to be 3 squared is 9. Alrighty. Now the bottom, just to kind of, since we all know where that's going to end up going, I'm going to write it just a little funky so you can see it and get used to it, okay? You all are going to write what? Cube root of? Probably 27 is where your instinct's going, right? I'm going to write it as 3 cubed. Okay? The logic there, yes? Yeah. You have 1 3 here. You have 2 over here. These are the same basis, so you add the exponents. 1 plus 2 gives you 3. Okay? You could, but yes, you could, but just hang tight, okay? You don't, exactly. Which comes in handy later. So we got 2 cube root of 9 over 3. That's it. Alright, so 4th root of 6 over 5x. First step is always split that from 1 radical. If they give it to you as 1, split it in 2, okay? Sometimes they'll give it to you as 2 right away, but sometimes they won't. Okay? Sometimes they won't. Okay, now, here's one, and this is once you change them line of thinking. It's like, once you understand why you're doing what you're doing, these problems are super, like, I hate to say the word, but they're super easy. Okay? Like, think about this real quick. All right, I'm going to ask you that W question here real quick. What was it, 3 over Rad 5, right? Whenever I asked you guys why we did Rad 5 over Rad 5, you said it was to make this denominator be 25, right? So it was a perfect square, which got rid of the radical. Okay? Now, 25 you can also say is 5 squared up here, all right? Instead of saying 25. And the square root cancels at that square power. Same logic. Okay? So down below, on the new problem here, we have the 4th root of 5x in the denominator. So how many 5s do we have here? 1. What's our index? 4. So we need how many more 5s? 3. Good. So the 4th root of 5 cubed. And it's going to come along too. I was just going to do my whole cube. How many here, how many there, how many do we need thing next, if that's okay. All right, cool. Here we go with that. Now for your x's, how many do we have here? 1. How many do we need total? 4. How many do we have to add in? 3. You see how beautiful that was?
So it's not 5x cubed, it's 5 cubed x cubed.
5 cubed x cubed.
So you have to do everything in there perfectly.
Yes. Because sometimes, and do it this way, because sometimes the variable will start with a different power than what your number will be at. Okay? Because if this was x squared, you would only need 2 x's here, for example. Okay? So always just do whatever makes these exponents all add up to be that index. Okay? Everybody good? Okay, now, take it a little bit step further, all right? I'm going to do, what do I want to do first? I'm going to do my denominator first. Okay? Because I want you guys to kind of see how you write this. So we have 1 5 and 3 more 5s. So that means we have how many 5s total? 4. Okay? So write that as 5 to the 4th. Don't worry about what 5 to the 4th power is. You don't need to. Okay? You really don't need to, because once you 4th root that 4th power, it's gone anyways. So there's no need. So there's no need to stress yourself out with that huge number. By the way, if you're curious, yeah, 625. So that way you don't have to worry about going back and figuring out what the 4th root of 625 is. You don't cause yourself that headache from a big number. And trust me, these numbers down here can get big. All right? So do it as a base with a power. You'll see on the next one, okay? Which becomes, and this is x to the 4th here. All right? Everybody cool? Okay.
So, are you not?
Yeah, your numerator, you had to multiply it all out.
So it's 750.
750, yeah. Yep.
Wait.
Okay. Everybody good?
Yeah, I took the 750 out.
All right, so we are right here. Okay? Everybody see that? Next step is to get these simplified, which entails a lot. Okay? It entails 4th rooting your denominator. That's the easy part. It entails factoring this up here, which can be the hard part. But follow your workflow. You had a 6. 6 factor trees are what? 3 and 2. Okay, so we have a 2, a 3, and we added in how many 5s? 3. So we have a 2, a 3, and 3 5s. Are there any groups of 4? No. Okay, so it's 750. So your answer is the 4th root of 750 x cubed over 5x. All right. Somebody walk me through it. First step. Homicide travel. Medora! Hold up. Don't. Hold on.
The dot for times and then the line.
I split them up first, but I'll go with that, okay?
And then, whoa, you're going really quick.
Yeah, I'm good, man.
Then you do 5 red 4 to the 4th, y to the 4th.
Do it
on the bottom, and then on the top you do 4 to the 4th, y to the 4th.
Good. Okay. Ecker.
Oh, no, I was right.
No, too bad.
No, I did it wrong.
Oh, I got it.
All right, Dimitri, keep going.
And then you times that, and on the bottom you have 4 to the 5th, y to the 5th, and then on top. Did you already?
Nope, don't worry about it.
Yeah, he did. He already did it.
Okay, in the top you get what?
5 rad to the 768 y to the 4th.
Y to the 4th. Can I take it from there?
Yeah.
Great. Okay, so from here, your denominator is real. He did a great job, by the way. All right, that's all right. From here, you have to take the 5th root of the 4 to the y of the bottom, okay, which will give you 4y in the end. But you have to check that 768, and you have to factor tree it. Now, I'm not really familiar with 768's factors. Now, I don't know about y'all, but I'm not. So I went by 2's. Okay, so by 2 and you get 384. All right, that's great. By another 2 you get 192. Cool. Another 2 you get 96. Anybody bored yet? By 2 you get another 48. By 2 you get another 24. And then 24 you go 2 and 12. And then 4 and 3, and that 4 goes 2 and 2. But makes sense? Okay. Now we're looking for groups of 5 since we're dealing with the 5th root. 1, 2, 3, 4, 5. Okay, so we're right here. So those 5 2's come out as that 1. And then we check the bottom of this tree that you can barely see. But we have a 2, a 2, and a 3. No more groups of 5. So we put them all back together as 24. Okay? So you put them all back together as 24, put it inside the 5th root of 24, y to the 4th, all over 4y, and then even if you get that far by some modern miracle, you're still not fully correct because what can you still do?
2 change to 1, 4 change to 2.
Reduce the 2 and the 4, exactly. So your full-blown correct answer here is the 5th root of 24y to the 4th all over 2y.
That was a very weird thing.
It was easy stuff to do, but it was a lot of stuff to do.
You're right. Especially factor treeing 768. That was almost a pain in my rear. Okay. Makes sense?
Yeah.
Everybody cool with all that work?
No.
Yeah, me neither, honestly. I'm not.
Shortcuts.
Yeah, oh gosh, yes. Okay. You know why there's a shortcut up there?
Because there's a 6 and an 8.
No. This is me doing it the second time because I love this stuff, okay? What's 4?
2 and 2.
Which is also known as a
It's perfect square.
perfect square. Okay. Now, when I said you need to know your perfect squares and your perfect cubes, it's not just because I love torturing children.
Well, you do though.
I do, but it's not all of it, okay? Now, watch this.
I'm watching.
4 is 2 squared. Y is still y. Nothing you can do about that. Okay? So the 5th root and the 5th root. Okay? Y doesn't change. You still have 1 y here. We'll still need 4 over here. How many 2's do we have here?
2.
2. We need 5 total. How many more 2's do we need? 3. Now, watch this. Down below, we have 2 squared times 2 cubed, which will be 2 to the 5th. 5th root of 2 to the 5th is 2. Y times y to the 4th is y to the 5th. 5th root of y to the 5th is y. What's 3 times 8?
That's rounded.
Your choice, folks. You can either go through this lovely misery, or you can just recognize that 4 is a perfect square.
That only works with perfect square.
Yes, it does. Okay, that is correct. Okay, if you're and here's where everything kind of ties in. I'm not speaking of this of 100%ness. Okay, there are cases where this can happen, but typically, when your denominator, actually, this probably goes always, but when your denominator has a perfect square, perfect cube in it, chances are there will be some reducing you can do at the end if you do it long ways. And I'm talking about this 2 and 4 right here. Okay? That'll happen. That means they'll be having the factor tree out of the numerator, however big that might be. That'll happen. Or you can just know that your perfect squares and perfect cubes and take this approach instead. Okay? It's not that I need you guys to know that 125 is 5, is cube root of 125 is 5, to be honest. Okay? I honestly need you to go the other way. Okay? I need you recognizing that 4 is 2 squared. That 125 is 5 cubed. Okay? Because imagine a problem like this, and there's the potential to this. What if, everybody good up here? Okay? I'm not going to work this because we still got another type to do. But think about a problem where I made it 2 over the 4th root of 125. Real easy answer. Ready? I already know it. It's 2 times the 4th root of 5 over 5. That's all it is. But I know that because I know 125 is 3 5s. And I only need one more. Which means all I need to do to rationalize this is times it, top and bottom, by 4th root of 5. If you don't know that, you're going to multiply, and you're telling me you're actually going to work this out by multiplying by 125 3 times? Good for you. Good luck. Okay? You know those, and those are the numbers I'll use here. Okay? Either those or some incarnation of 2, like 32, or 16 maybe. Stuff like that. Okay? I'm not going past 216 though. Alrighty? Make sure you know those. If you didn't know them today, make sure you know them. Alright? Let's go last type. This is easy stuff. We didn't do one with you guys. That's it, right? Yeah. This class didn't do it. The other class did. It was on their old section, so I'm going to tell you this. This problem should look somewhat familiar to you. Okay? You know how to do this. You just don't know how to do it in this context. Okay. It's still a division, so we're still rationalizing, right? Which means we still need to get rid of the radical. So, what are your thoughts? What are we thinking here?
Still multiply by rad 5 over rad 5.
So, rad 5 over rad 5. Okay, let's think about this now. If we did rad 5 over rad 5, I'm going to write it down here. We would distribute this rad 5 in here.
Oh, no.
Rad 5 times rad 5 is 5, minus a rad 5.
Do you have to do the conjugate thing?
Good job, Ecker. Good job. No problem. Do the conjugate. So if I give you rad 5 minus 1, rad 5 plus 1. Top and bottom. The top becomes what? Starts with a D? No.
Dividend.
No. Distribute. Bottom becomes what? Starts with an F.
Factor.
Foil. It's binomials and binomials. Come on now. Alright. So the top, you go 2 rad 5 plus 2. Over the bottom, rad 5 times rad 5. I'll write this out this way. It's rad 25. Let's see here. Plus rad 5 minus rad 5 minus 1. Okay. So I'm going to change this order too just because I'm OCD. I need my numbers. If it's like this, I must have my number first. My rad second. I don't know why I'm weird. I know. Okay. Rad 25 is 5. Right?
Yeah.
5 minus 1 is 4. Rad 5 minus rad 5 is 0. Okay. By?
The 2.
Good. Okay. So what's it become? No.
How'd you get 2 rad 5 over 2?
No.
2 rad 5 plus 1 over 4.
No.
Rad 5.
There we go. Okay. Now, I'm going to show you guys the why this works this time, okay? It used to just be if it's in a V, it cancels out, okay? I'm going to show you guys why this actually works here. This 2 plus 2 rad 5, what's the GCF for these two terms? 2. Okay? Your GCF there is 2. So 2, parentheses, 1 plus rad 5, all over 4.
I'm confused on where you got that. Wait. Oh, no, just kidding. I was, say rad 5 plus 1 over 2.
That's fine too, yeah. X times rad x, here we go, x rad x, plus x times 1 is x, plus 1 times rad x is rad x, plus 1. Okay? Over. Rad x times rad x at the bottom gives you rad x. The middle 2 will cancel, leaves you as minus 1. Now, I put this problem on here on purpose just to kind of yank your chains, kind of. All right, and to show you kind of the logic of where we're heading. Okay, because what I'm about to do, I really don't expect you to recognize yet. Okay, for you guys' purposes, if you got that far, I'm tickled pink. All right, but you're not done yet. To be completely honest, does anybody see anything?
Yes.
A lot of X's. Okay.
Negative and positive.
Olivia.
You can add the x rad x and the rad x.
Yeah.
You can add the x and the rad x together.
But there's no.